Let me start out by explaining the awesome title of this talk. I just got back from a year's sabbatical at the Technion, which was funded by a Fulbright fellowship. Fulbright is a U.S. government organization. And one of the conditions for this fellowship is at the end of the year, you have to put together a talk that explains to a general audience what you've been doing with the taxpayers' money for all this time. And so what I'm going to present here is a somewhat modified view of that talk. Normally, I'd like to talk about more technical things, but since I have this kind of high-level talk prepared, I thought it would be fun to try that here. So when I talk about before I can talk about the future of distributed computing, I have to get the software to work. Why is my machine frozen? Okay. There we go. Okay, so what I'm going to do is I'm going to give you an overview of and very much simplified history of distributed computing and what's been going on for the past number of years. So I'm going to start out with the state of the field as it was when I first got my PhD, back when distributed and concurrent computing was respected in the sense that people would say, oh, that's very interesting what you're doing, but it wasn't really taken seriously. Because as Bill said, there weren't really any machines and nobody's livelihood really depended on anything that we did. So the principal conference in this area is called PODC, Principles of Distributed Computing. And the first one I went to was in 1982. And at the time, what we were doing was science fiction, in the sense that operating systems conferences talk about real operating systems. Networking conferences talk about networks. But distributed computing talked about things like replication, remote this, that, and the other thing, large-scale things that didn't really exist at the time. And everybody said, well, but it's inevitable that in the future, we will have parallel machines. It's inevitable we will have large-scale distributed systems. It's inevitable that we will need a replication to get fault tolerance and so on. Of course, nobody was more surprised than us when this actually became true at some point. But it was really it was all kind of speculative. So now, and as I said, the reason is that parallelism didn't really matter to anyone who was doing computing for money. Nobody's job depended on whether we could improve things or not. And at the time, as Bill was saying, there were all of these computer companies, Sequent, Encore, and so on, that made a big splash by coming out and saying, we're going to give you an 18-processor machine. But the truth is that by the time they got all their cache coherence protocols working, they managed to speak the right bus protocols and so on, Intel would sell you a much cheaper chip that would do everything much faster, completely sequentially. So parallelism research was really kind of a hothouse flower. Now, in a talk like this, it's obligatory to have a Moore's Law slide. They've got to have it stamped on my passport, so they let me out of the country at the airport. And as you know, Moore's Law says that processor speed over time goes up, transistors on the chip goes up. And but what people don't always realize is that Moore's Law is really this curve. It says you always get more transistors. The fact that the clock speeds went up proportionally was kind of a coincidence. And so, but at the time, what would happen would be what people call the free lunch. So that at some point, everybody who needs an operating system has one. So what you want to do is you sell upgrades. You sell new things. New things make your software slower, puts more burden on your hardware, but you don't need to worry because 6 months from now, the clock speeds will have speeded up so much that you won't notice any difference. And you really will get more value. So you can always just throw new stuff into your software, into your operating systems, and things automatically get better. And again, because of this phenomenon, distributed computing, although everybody agreed that these were, yes, indeed, interesting and profound problems, was really kind of marginal to mainstream computer science, because people did perfectly well without any of our wonderful algorithms. Okay, but now things have changed, as you may have heard. So everything started out in 2004 when, in a little-noticed announcement, Intel basically said, well, we've given up trying to make the Pentium run any faster. They canceled this huge project, and this was really a kind of a turning point in the way that modern hardware works. They said, from now on, we're not going to try to increase the clock speed every year because we can't. And so what's happening now is that the transistors on the chip are going up the same way that they ever did, same way they always did, but the clock speed is basically flattened out. So that the laptop you buy next year won't be significantly faster in terms of clock speed than the laptop that you bought last year. And the question now is, well, but what's improving? What do we have more transistors, but they don't run any faster. What can we possibly do with this sort of thing? Now, the problem is that a modern processor is a lot like the 1975 Volvo that I used to drive as a graduate student. You put it in gear and head down the street, and if you press on the gas, beyond a certain point, it doesn't go any faster, but it just gets a lot hotter. And so the problem is that if you try to increase the clock speed on modern processors, they get hotter. And for various profound reasons of physics that I don't understand, it's basically impossible to cool them off. So we're stuck with the clock speed. So instead, what we do is we take our old uniprocessors and we replicate them on something called the Multicore. So this is a Niagara. These boxes here are processors. Everything else is caches and interconnect. But here we have 8 copies of the processor, and this is kind of a dated chip anyway. So what manufacturers are doing with all of these extra transistors is they're giving us more chips, giving us more parallelism. So each chip runs at the same speed it did last year, but next year you're going to get twice as many as you got this year. And the question is, what are the implications of this? Well, the implication is basically that the old order, where you could add new functionality, and 6 months later you could reap the benefits but not pay anything, so that old order lies in ruins. If you want to ride the technology curve now, then what you have to do is you have to use more parallelism. You will have more threads available, and you have to figure out how to make use of that. So if I'm writing an application, I have to say, well, next year I'll have 64 threads, and the year after that I'll have 128 threads. How can I deliver more value with that? And the sad truth is that when it comes to the question of exploiting a parallelism, nobody really knows how to do this. Despite what people might tell you, it's still a kind of a mystery. People make progress in certain areas, but as a general challenge, this is still very much an open question. And it can be, if you're looking for kind of a long-term research challenge, then this area is full of things that you can do. Now, if we go back to distributed computing research, what you'll see is that it's no longer science fiction. We're now talking about the same thing that everyone else is talking about, which is incremental improvements on things that already exist. What may be less obvious is that these topics are actually the same thing that we were talking about back in 1982, except instead of calling them parallel algorithms, we call them multicore. Instead of calling them distributed computing, we call them cloud computing or peer-to-peer services and so on. But it's the same basic ideas, sometimes the same people. And my colleagues have basically 2 kind of responses to this. One is, well, it's about time. All these years of the systems people kind of looking down their noses at us, finally we're getting our revenge, and suddenly people actually want to talk to us. But I think it also works both ways. in the sense that we also have a responsibility, now that it matters, to make sure that what we're looking at in the distributed computing community actually has some bearing to the real world, now that there is some chance we might have an impact on it. So with great relevance comes great responsibility, or even minor relevance. Okay, so again, some of my triumphalist colleagues think that the world should be grateful to us for working on these things for so long. So you can say, well, what this really is this is a renaissance of distributed computing. Now that Multicore has taken all these issues we studied for so long and suddenly made them appear relevant. But another is that it's more of a call for reformation. That to some extent, for a long time, working on problems that didn't actually correspond to real machines and real problems, there's no corrective. And you can sometimes go off and do model abuse, and you can sometimes spend a lot of time going down rat holes and looking at problems that are maybe of a great academic interest but less practical interest. And so it's kind of the balance between these two approaches that I want to talk about. So let's look at the sort of near future of my field, and what are the things what are the big challenges? So imagine that you were in charge of some large semi-monopolistic corporation. I'm thinking, of course, of Tim Hortons. And you're worrying about what is the problem, what problems are we likely to face in the future? Well, the problem here is basically that if I can't make things a lot better by adding more cores, then why would anybody ever upgrade? Everyone who needs a laptop has one. Everyone who needs a complete office suite already has one. And the only way we're going to make money is by upgrading to fancier models. And if I can't actually make something that works better, that can exploit the parallelism, exploiting clock speed was easy, but exploiting parallelism is hard. If I can't do that, then how are we going to stay in business? And really, somebody at Microsoft explained to me that they're worried that computer science might become like washing machine science. In the sense that if your washing machine breaks, you don't turn in your washing machine every 2 years for a better washing machine. You keep it till it breaks. Because it's true that every 2 years you can buy a better washing machine, it's not much better. So it was the case that 2 years you could just throw your laptop or your mobile phone away and get a new one, even if the old one wasn't working, because the new one was so much more awesome. But it's no longer quite as clear how to do that. And in particular, your kids are not going to stand in line all night outside of the Maytag store waiting for the latest washing machine release. Okay, so you might say, well, I'm an academic. Why do I really care about all this real-world stuff? Maybe I prove theorems for a living or something like that. And the answer is that really, no matter what part of computer science you're in, the sense of excitement and so on that we have really comes from Moore's law. The fact that every year we can think of doing something we couldn't do the year before is what gives us the best students. It's what gives us funding. It's what gives us prestige. It's what adds excitement to the field. And without this, we might be just another engineering field. I used to cite specific engineering fields as being exemplars of boring and stagnant things, but I've learned not to do that. But imagine that you were in charge of building steamships, that kind of thing. So the fact that the engines that drive computer science are stalled because we can't deal with parallelism is something that everybody should be worried about, even if you don't use multicores directly in your work. So here's the heart of the problem. So a lot of work on parallel computing, especially scientific computing, you divide the world up into parallel parts and they all go off and work by themselves. And really that part of the world, this so-called embarrassingly parallel part of the world, is in reasonably good shape. The problem is that you can't always structure your code in such a way that everything can go on in parallel without any kind of coordination. Sometimes your activities have to synchronize with each other. Sometimes they have to exchange information. Sometimes they have to agree about who goes where, that kind of thing. And this is the part that is the critical problem with things like multicores. It's a synchronization. And the part of this is something called Amdahl's law. I'm not going to give you the quantitative form of it. Basically, it says that you might have a program that is overwhelmingly parallel, but if the little bit of synchronization you need to do is done badly, then overall your performance is going to be terrible. Amdahl's law is a very cold and a cruel rule that says that the sequential part of your program is going to dominate its performance, no matter how clever you are about the rest of it. So that doing a synchronization in a bad way is really the obstacle to making things like making multicores and concurrent programs work well. So what I'm going to focus on for the rest of the talk are some approaches to doing concurrent data structures. So you think of concurrent data structures as the ball bearings of a machine. My bicycle has lots of moving parts that move independently of each other in parallel, but if the ball bearings aren't done right, then the bicycle as a whole isn't going to work. And the same thing is true of most parallel programs. If the synchronization and coordination part doesn't work, then the vast amount of parallel parts you might have sitting around aren't going to help you. Okay, so I'll say a few words about old school synchronization. That is the way that we've done things up till now. Now, I think it's a measure of how irrelevant parallel and distributed computing was, is that kind of the standard techniques that we use haven't changed much since the 60s and 70s. You know, we're still using ideas that were developed in those times, and the fact that those ideas are all fundamentally broken didn't bother anyone because it never really mattered. And suddenly we're discovering that all these things that we learned about in our beginning operating systems class really don't do what they're supposed to be doing. Got another software freeze here. Okay, so the simplest way to synchronize a concurrent data structure is you put a lock on it. The easiest way to do this is what's called coarse-grained locking, where you put one big honking lock on the entire thing. So the Solaris kernel, for example, used to have a single lock that controlled the entire thing. And it took them years and years to fix this because, frankly, they were afraid of fooling with it. Nobody really understood how it worked, and this was a very important commercial product for Sun. And so it took them a long time to replace it. But clearly, coarse-grained locking isn't scalable. You put a single lock on a big part of your system, then there's no possibility of concurrency. So the next thing you can do is say, well, I'd like to break things up into lots of little locks. You know, that's an easy thing to say, but hard to get this right in practice. And there are all kinds of problems, performance problems, debugging problems, deadlock, all kinds of things. And it's relatively, I teach a course on this, and I've written a book on how to do this. And it's easy to show a buggy algorithm on a slide to a bunch of smart undergraduates, and it takes some convincing to convince them that it's buggy. So imagine how this works out in the real world. So one problem with locking of any kind is that locks aren't robust. That is, if some thread takes a page fault and goes on vacation for a few million cycles, then if it's holding a lock, nobody else can make progress. The similar kind of problem that people don't often realize is that locking is based on conventions. That is, the relation between the lock word and the data exists only in the mind of the programmer. So this is an actual comment from the Linux kernel. I don't know what it means either, but it's kind of scary because it's clear that if you do this wrong, bad things might happen every once in a while, and and of course there's no guarantee that what it says is still correct. But this idea that everything relies on the goodwill of Finnish teenagers is a little bit scary. A similar kind of... The other claim that I want to make is hard to quantify, but I think you'll know it when you see it, which is that it's just hard to use locking effectively. So here I have sort of the homework problem from hell. I actually tried to give this as a homework problem during my first year as a faculty member and learned this was not a good idea. So here I have a queue. It has two ends. I have one thread that wants to do an NQ and one thread that wants to do a DQ. And the question is, what kind of locking do I want? I could put a lock on the whole thing, but that's not scalable. So what I would like to guarantee is that if the ends of the queue are far enough apart, then the NQ and the DQ should be allowed to go on in a parallel without interfering with each other. But of course, if the queue has either 0 or 1 elements, then they had better synchronize. If there's one element, they've got to decide who does what to it. And if similarly, if it's empty. And so in that case, it's okay to have a synchronization. So interference is okay if the queue is small. Interference is not okay if if it isn't. And if you can come up with a nice clean solution to this very problem, I think it's publishable. It's probably not publishable in a first-rate conference because this has already been published in a PODC in the 90s. And this is Mogin Michael and Michael Scott wrote this paper. But it's a little bit of a scandal that this very simple problem, which you could explain to a high school student, is basically a publishable result. So if you talk to mathematicians, they gloat over the fact that they can give you, the number theory people can give you these simple statements that take centuries to prove. And nevertheless, I don't think we should be gloating over the fact that we can give you simple data structure problems that take decades to prove, because we have aspirations to being an engineering field and doing kind of more practical things. So I'm saving the most serious problem with locking for the last, and that's composability. So one of the first things we teach students when they write programs is no, you don't have to write your own cosecant routine. We have things called libraries. And you can call the library and compute things like cosecant and square root without knowing anything about the implementation. I can take the square root of the cosecant of something, again, without having to worry about what's inside. But the same isn't true of lock-based synchronization. So if you write a program, say, in Java or C#, they encourage a style where each method has its own internal locks. So I write a queue, NQ, first thing it does is synchronize method. It requires a lock, does its business, releases the lock. Similarly for a DQ. And now I have two FIFO queues, and each of their methods have internal locks. And now what I want to do is I want to atomically take an element from this queue and put it over here. And I want this to be done indivisibly. That is, I don't want to see two copies of that object, and I don't want to see 0. I want to see that it's either in one queue or in the other queue. And basically, there is no reasonable way of doing this using current locking practices. So if the locks are internal to the methods, then you can't get at them. If you export the locks, then you've just blown away any kind of software engineering modularity, because now correct use of your abstraction requires that all of your clients behave. And anybody who fails to follow the right protocol is going to break things. So this is really bad software engineering. So the last critique is that locks just don't compose. Okay. By the way, if anybody has any questions or objections, if you think this is so outrageous you can't stand it, then speak up, and I'll be happy to respond. So what I'm going to talk about now is, now I'm transitioning from, so I've gone from totally conventional wisdom to slightly outrageous opinion, and now I'm going to be talking about my own opinion, which not everyone else agrees with. And I'll give you some of the dissenting views toward the end. And that is, everyone who works in systems, and this is a secret, so don't tell anyone, knows that all the main principal key fundamental ideas in systems were stolen from the database world. That everything systems people have ever done was invented in the 70s in the Jim Gray's System R group at IBM. Fortunately, their papers are written in IBM jargon of the time, which, as far as I can tell, is not an Indo-European language. So they IPL something instead of booting it. It took me a while to figure out a DASD is actually a disk, that kind of thing. But as a result, many of us can make a living by taking their ideas and recycling them in new contexts, and no one ever suspects. So the idea that we're going to borrow is the notion of an atomic transaction. So syntactically, we'll just say a transaction is a block of code surrounded by this keyword atomic. The meaning is that this code is executed atomically. That is, nobody else can see an intermediate state anywhere between the beginning and the end. And yes, there are a lot of subtleties having to do with this definition, but I won't.
I think the mic's going to.
Yeah, I think so too.
Yeah, is it a battery problem with the mic?
Hello? Hello?
Yes, because there's feedback or something squirrely.
Okay, so I won't walk near that.
Or if it gets worse and you just want to rip the mic out and just talk, that might work.
Mm-hmm. Okay, I'll try that. Okay, so the idea is that you can do this without worrying about deadlock, live lock, fairness, and often the implementation will be speculative in the sense that we'll try it. If something goes wrong, we'll roll back. Sometimes the speculation is invisible and sometimes it isn't. So the terminology is that if the speculation is successful, we say the transaction commits. And if the speculation is unsuccessful and has to be rolled back, we'll say the transaction aborts. So that programming problem that I gave you before, where we want to guarantee that these that work at different ends of a queue can go on in parallel under certain circumstances, is trivial in a transactional model. You simply take this is what the NQ method looks like. You just say that it's atomic. And it's up to the implementation to make sure that works. So you just take your sequential code, slap atomic around it. And that almost always works. The problem of atomically moving an item from one queue to another is also trivial in this model, because you can nest transactions. So here I just say atomic, and then I dequeue from one, enqueue to the other. And the atomic keyword guarantees that nobody sees an intermediate state. So transactions, unlike locks, compose, because in some sense the mechanism is transparent to the runtime system, which was typically not true of locks. Now, of course, there's an enormous number of research papers dedicated to exploring the subtleties and possible contradictions and gaps and so on in this model. But largely, these are second-order effects. Most of what I've said about this solving all your problems is sort of kind of true. There's still an enormous amount of research that can be done to plug in the holes and fill in the gaps. But this does address many of the problems that locks raise. So one place where these ideas have shown up is in a lot of recent programming languages. So as you can see, there's Clojure, this is Python, Java, Camel, and so on. A lot of these languages either have transactional model, which is typically called transactional memory, built into them, or they provide libraries to give you the same thing. So in terms of languages and compilers, this idea is kind of moving into the programming language mainstream. But there's still a lot of programming language issues that are not well understood. Okay. So there's still a lot of programming language issues that are not understood. Can everyone hear me? Okay. The biggest one is how do transactions interoperate with non-transactions? If you go to Intel and you try to sell them this, they sell, well, we've got 50 years of legacy code. What happens if one of your transactions tries to interact with a thread that doesn't know about the transactions? Speculation and side effects. What happens if I go inside a transaction speculatively and launch a missile and then decide I want to roll back the transaction? How do you make sense out of that sort of thing? All of these problems I'm giving you there have been published papers with proposed solutions, but I think it's still up in the air. It's not the case that anyone has universally agreed on things that, on approaches that work. Conditional waiting. So I'm in the middle of a transaction and I read from a buffer and discover, oops, this buffer is empty. What I really want to do is I want to consume something. What I want to do is I want to wait until something shows up in the buffer, but I can't do that atomically because I've already seen the buffer's empty. So how do I deal with that? And there are lots of proposals about rolling back the transaction part way until the buffer fills up and then going forward, things of that nature. That's also still a big open area. So another question is, how do we implement these kinds of transactions? In this case, this is work on compilers. There's a group consisting of Sun, which is now, of course, Oracle, IBM, HP, and Intel have issued extensions to C++ compilers that have a more or less kind of compatible transactional interface. We say underscore atomic and so on. And these are different papers that talk about this is the Oracle, this is Intel, and so on. And so you can now download these compilers and experiment with them if you like. And so standardization is a big deal because it's hard for people to agree on things because the area is so new, and yet you don't want to have to write a different benchmark for everyone's compilers. There are emerging suites of benchmarks that come out now. Stanford has something called stamp benchmarks, which are fairly widely used by everyone. And of course, the question of how do you optimize this so it runs quickly enough is an issue that I'll return to soon. There's also a lot of work on runtime systems, so-called software transactional memory structures. Issues here are, well, you can do same thing database people have been working on for generations. You can update things in place, or you can keep a record of what you want to do and then apply it when you commit. Which one works better? You can detect conflicts as they occur, or you can be more optimistic and detect them at the end. Which one of these strategies work best, and how do they interact with the others? If you want, read-only transactions are considered important. How do you allow read-only transactions to interact with everything? And as you can imagine, the number of interactions is growing enormously with each of these design issues. And in fact, there's no consensus about which of these approaches work. There's also hardware transactional memory. So this is the Sun's ROC chip, which supported atomic transactions in memory. It had a machine instruction that said begin transaction. You could then execute a sequence of steps, not too many, but not too long. And then you could commit your transaction. Basically, you did this by playing games with cache coherence protocols. So you can make tentative updates in your L1 cache and then write it back to memory when your transaction is committed. And this is a paper that basically describes your experience with hardware transactional memory. So that's the design and use of hardware support for transactions is also a big research area. There's a whole bunch of papers on how to build a hardware transactional memory. Should you be limited by the size of your L1 cache? If you overflow your L1 cache, do you just give up, or do you try to overflow gracefully into other caches, things like that? How does transactional memory interact with your memory model, that kind of thing? So here, too, there's a growing literature, but there's still, I think, a huge amount of opportunity and work that could be done. So, again, we exploit cache coherence. We need to worry about what happens when timer interrupt comes in and cleans out the cache from underneath us. So is it possible to save your transaction to get back to it? Is it worthwhile? There's a whole section of work on something called lock elision. So here the idea is that if your processor is smart enough to recognize, oh, this is the start of a critical section, and then look down your pipeline and say, oh, that's the end of the critical section, and these two things aren't that far apart, you could say, well, instead of actually acquiring the lock and releasing it, I'm going to try to do the whole thing as a speculative transaction. And the advantage of this is you don't have to, it's invisible. It works on legacy code. It works on code where you don't even have the source. You don't have to retrain your programmers. And this is, I think, the aspect of the transactional model that's probably most of interest to people in industry. I'll say a brief word about energy. So I have a project with some of my colleagues in engineering where we look at basically embedded devices that have embedded multicore devices that use transactional memory for synchronization. And the question is, does transactional memory improve your energy performance over locks or not? And the answer is mostly it seems to. Okay, so coming up on the end, I thought I would tell you some of the dissenting views. So I think I have a responsibility not just to tell you what I think, but to point out some of the places where people, mostly of goodwill, might disagree with what I'm saying. So I'm going to show you some of the objections to all of this to everything that I told you. First thing is some my colleagues in the Solaris kernel group basically say, well, you know, we've been writing fine-grained concurrent code all our lives, all four of us, and you know, we've never had any problems. So what's all this fuss about? You know, why bother with all of this stuff? And so basically, they say that the whole question of crisis with concurrent software and reasoning about parallelism is so much hysteria that we're doing it just fine and we don't need any additional mechanisms. So, you know, if you buy into this, then there's not much you can argue with. So another one says, well, trying to replace locks with transactions is doomed to a failure. It's possible that transactions are easier to reason about than locks, but the truth is, programmers are just too dumb to get it. That you know, most programmers you know, just can't be retrained. They've learned about monitors and the condition variables, and you know, as soon as they graduate from college, their minds freeze, and you know, you're doomed if you try to introduce a different model, even if it's a simpler model. So here too, I'm kind of skeptical about this argument, but I thought I had to mention it. My favorite counterexample is more of a kind of a Marxist critique of transactions. So it says that programming in shared memory is basically evil and doomed, and must stop as soon as possible. The problem with transactional memory is that it makes shared memory easier to use, and therefore prolongs the time until the great crisis of shared memory, when message passing will rise up and rule over the world. And so the idea here is that transactions, by making shared memory easier, just you know, encourage people in their bad habits. Now, whereas I'm actually, you know, I like Erlang and that kind of a thing, I think the distinction between shared memory and message passing is a little bit overblown. Because once a program reaches a certain size, the two are kind of indistinguishable in terms of the problems you have organizing and reasoning about it. That the real problem that Erlang addresses is mutability, that you don't have things in your memory changing out from underneath you. But there are other ways of fixing that problem without taking this kind of extremist position. So the one critique, which I think is the most cogent and the one that we need to worry about the most, is the question about whether software transactional memory is too inefficient. So the truth is that research prototypes that do software transactional memory are slow. You know, they're much slower than they should be. They get faster every year, but they're still slow. So one thing is to say, well, okay, so maybe hardware could come along and help us. IBM recently announced hardware transactional memory on Blue Gene. Wouldn't surprise me if other major manufacturers were to announce support for hardware transactional memory in the foreseeable future. And so the question is are transactions more like garbage collection or more like virtual memory? So virtual memory seems like a great idea. It's simplified all kinds of programming problems, but it was unusable until people put in hardware support. Garbage collection was also viewed as being unusable and inefficient, and many people thought that you needed hardware support. And in fact, the i86 architecture has some instructions that were inserted in there to make garbage collection go faster. Intel engineers are still bitter about this. And it turned out not to be needed because over time people learned how to do garbage collection well enough. And so depending on which analogy you believe, then maybe hardware will make things more efficient, or maybe that over time software will become efficient enough that people will be happy with it. Okay, so I'm going to do sort of a brief survey. I promised you the sun, the moon, and the stars, and you can say, well, okay, but has anybody done any studies showing that this actually works? And the answer is sort of. So in this paper right here, this is the one where we looked at hardware transactional memory for embedded devices. And what we found was mostly hardware transactional memory is more energy efficient because you can do everything in your L1 cache. You don't need to go all the way to a memory unless you need to roll back a lot of transactions, which is energy inefficient. But it's hard to do that. Another issue here is there's a group in Texas that went through and used transactions to restructure the Linux kernel. And so what they did was use lock elision. That is, they would replace critical sections with speculative transactions. For most locks, not all, some locks would be acquired by one thread and released by another thread, and that was too hard. But the vast majority of locks were pretty straightforward. And they solved the problem of I/O by if you were in a speculative transaction and you tried to do I/O, it would roll back and acquire the lock and do it again in a non-speculative way, transparently. And they were happy with that. There's a lot of interesting research on interactions with the scheduler and residual locks. That's mostly what the paper is about. And they ended up with something that they thought was better structured but comparable performance with the standard kernel. Now, another group at Harvard and at Sun went through and put transactions in the Berkeley DB lock manager. This is a highly multi-threaded program. The lock in Lock Manager isn't the same as the locks that I was talking about before. They're group-based database locks. And what they found was that it wasn't all Skittles and beer. So originally, I think they thought they could just find every critical section, turn it into a transaction lesson, and let it go. But it turns out that if you do that, there's all kinds of false sharing, or false conflicts that happen. In particular, there are performance counters everywhere. Berkeley DB increments counters every time you sneeze. And these counter increments were viewed as data conflicts, even though they had no effect on the actual running of the code. So it meant that you had to go through and figure out whether this particular compare and swap was something important that had to be in the critical section or whether it was a side effect that didn't. Oh, and malloc tree also made them unhappy. So the answer there is that you can't go through and take existing parallel code and transactionalize it mindlessly. That isn't going to perform very well. So Azul Systems is a company that sells humongous Java servers. And they actually have hardware transactional memory. And what they do is they use it for contented Java locks. So you come to a synchronized block, their just-in-time compiler will call the hardware transactional memory and run it speculatively, unless they figure out that that's not working. And what they found was that in some cases this worked really well. In other cases it was sort of meh, didn't make much difference. And in a few cases it made things worse. And their biggest problem was that there's all kinds of false conflicts. So when you call the built-in Java hash table library and you do something to it, it has a counter that counts the number of mutator operations, things that change the state. So even if you have two methods that don't touch the same memory, which should be allowed to go in parallel, they both increment this counter. Now the sad thing is that nobody ever beats this counter. It's a write-only counter. But somebody put it in there because they thought it was a good idea and they never actually used it. But what this means is this is sand in the synchronization stopwatch because it means you can't parallelize anything automatically here. And they did some experiments where they rewrote things, but it's very tedious to go through these libraries and do that. So again, they have a mixed bag. In some cases it works really well, but the residual false conflicts are worrisome. Another promise that people sometimes make is that, well, writing code with transactions is easier to do than locks. And so there are a couple of small studies that look at this. The same people who did the Linux kernel transactionalization took a bunch of undergraduates and they did a simple game application in Java. And they did 3 styles. They did one with single big lock. They did one with fine-grained locking done by hand with T-threads, actually no, in Java. And then they did one with a transactional memory implementation. And not surprisingly, having one big lock and using transactions was considered by the students to be roughly the same in difficulty, because you don't have to think about that very much. And fine-grained was a lot harder. But the interesting thing is, if you look at the mistakes that people made, here, because I'm talking at a high level of abstraction, I've erased all the labels, but these are 3 different tasks. And so you can see that fine-grained locks had huge numbers of errors relative to the other. Coarse-grained locks had a medium, and transactions were most likely to be correct, just because you need less brain power to do things. And one of the most amusing parts of the paper is they have a list of some of the errors that people made with fine-grained locks, which were kind of jaw-dropping in a few cases.
A quick question on that one.
Yeah.
So that data is from 147 undergraduate students implementing a simple game in Java, right?
You would never be able to use this to make the FDA would never accept this as a medication.
Well, no, the question I was going to ask on that is that, so that says that you get, in first cut, sort of the first round of writing the code, you have fewer errors in transactional memory. But if I want to actually ship a product, it's not so much the first errors I get at, it's how much work do I have to do to get it clean enough to ship? Is there any data on that?
No, what they did was they had each group implemented all 3, but they did it in random orders. So that for some of them, transaction was first and so on. So none of this is really scientific because the samples are small and so on. So I would not use a drug that was approved by this kind of experiment. But this is what we have. So there's another...
Second question.
Yes.
What kind of errors show up in the transactional?
So what they did was they took the code and they gave it to a third party and said, find mistakes in this. And the mistakes are mostly things like race conditions, modifying data without locks. So you have 2 threads that are both modifying something, and one of them has the lock, or maybe neither one has the lock. There were other crazy things where...
He was curious about the errors for transactional memory.
Oh, that I don't know. Either the paper was unclear about that, or I don't remember.
Sorry, just one more on this.
Mm-hmm. Yeah.
On this slide. Do they evaluate all the resulting performance or efficiency of the 3?
This one, there's another paper which was done in Germany at Paderborn, which I dropped from the talk just for time reasons. But they found that they used the Intel C++ compiler, and they found that the transactional one was actually considerably more efficient than the pthreads version. And it was basically the same kind of error distribution. It's still the case, the Paderborn paper is particularly sort of using on this, that there was one team of students who were apparently totally incompetent, and they messed up the transactional one just as much as the others. So it's not it's nothing magic. Bad programmers will write bad code no matter what. But the sort of medium level and programmers would seem to do better by this. So again, this is not a deep scientific study, but it is a kind of a systematic attempt to try to understand what's going on. And it is the only data point that exists. Other than the other paper, which I'm not going, which says the same thing, which I'm not going to talk about. Okay, so here's what I think the big picture is. So this is something called the Gartner hype cycle, which I think characterizes the behavior of any sort of controversial idea, where it starts out and somebody thinks of something and publishes a paper on it, and it may be obscure for a little while, and then suddenly people realize, whoa, this does something wonderful. This will drive me to the airport, make my mortgage payments, and make my house for me. And all of our problems will go away once this becomes widely adopted. And then there's a huge hysteria and acclamation. And And then after a while, people say, "Oh, wait a second, this isn't true. It's actually much more complicated." And then there's a kind of reaction. People say, "Well, I was so euphoric about this before, and now I feel so used when I realize that in fact there are other problems that this doesn't solve, or there are it introduces new problems and so on." And then, and I think the dissenting papers that I showed you earlier on were basically a reaction to this, because there was a lot of hype early on, where people, no one I work with, but other people, may have overpromised. And what happens though is that gradually, and much less dramatically, people, figure out how to solve these problems, and gradually, things become better and better, and then eventually. The very idea of like garbage collection, which used to be very controversial. I mean, I knew people when I was in grad school would spit on the ground when they heard garbage collection and talk about how it's the most ridiculous idea ever invented. And now, you probably don't even think about it when you write a Java or C# program that's garbage collection. In the same way, all these ideas gradually fade into normality. People stop publishing a lot of papers on them because it's no longer a hot topic, but that just means that the idea has been accepted. So I'll leave it up to you to figure out where on this curve we are. This is, I think, a good view of what's of the state of this particular thing. So for conclusions, I'll make a couple of predictions about where this kind of whole field is going to go. And again, I want to keep the focus on research areas that you might think about going into if you're, say, a graduate student looking for research area. So one thing is that there's all this fuss about multicore computing. And I don't think that's going to go away for a while. The nature will change. As multicores get bigger, they're going to look a lot more like distributed computing. And as cloud computing and sort of traditional distributed computing gets more civilized, it's going to look more and more like shared memory computing. So if you look at a program that uses something like MapReduce, and you don't look too closely at the syntax and think about the structure, well, it sort of looks like a shared memory program. Yeah. And that's going, as the tools get more high level, the distinction between these message passing distributed and the shared memory read-write is going to get harder and harder to discern. So if you write a shared memory multicore program as if it really was shared memory, you're going to get terrible performance. You have to know that underneath there is cache coherence protocols. You want to make sure your spinning is on local variables and so on. So you kind of have to outwit the abstractions underneath. And you can't do work in one area without knowing something about the other areas in some sense. But I will confidently predict that people are going to continue worrying about things like persistence. Transactional memory is not persistent, but cloud computing is nothing if it's not persistent. Caching, people will always be doing caching. Non-uniform memory is becoming more and more important because it's getting harder and harder to hide the latency as you build bigger and bigger multicores. And coherence is an endless source of confusion. So in all these things, there's a tension between sort of the nice, clean, theoretically pure properties that theoreticians love, and the pragmatic engineering stuff that engineers love. If you look at memory models, you'll see this kind of a tension between stuff where we actually understand what's going on and stuff that we can implement really efficiently. And either way, I think it's safe to say that for the time being, something called transactions will provide something called consistency. And what exactly that means is the focus of future research. Okay, so that's all I have to say.
So I'm going to ask this question a little bit obnoxiously. I think you made a very compelling case in the motivation that we have a future as Washington DC salesmen if we don't sort of harness parallelism properly. And then you made a really nice case also in terms of transactional memory as being better than locking. But the second part of your talk really wasn't answering the first question because, as you mentioned, Amdahl's law is a cruel master, right? And it's really about how much parallelism is really there not just can I program relatively easily the parallel parts of my program, right? So is there really, I mean, even with transactions, is there a hope to avoid the fate of the May-type repair? Do we have hope here?
Well, I think what I'm addressing here is, given that you understand how much parallelism you can have, what's the best way to fix that? The question of how to eliminate parallelism or reduce it isn't really something that I address, and of course that is hugely important. I don't think there's any kind of systematic way, because I don't know a systematic way to approach that. That seems to be more application-specific, domain-specific.
But certainly you talk to a lot of people. I mean, you must have thoughts on this. I mean, how optimistic is the future? Or is Amdahl's law going to doom all of this at some level?
Well, Amdahl's law is a little bit like the speed of light in the sense that you can't really...
Yeah, right, you can.
You know, and so the way people have traditionally gotten around problems like this is you weaken your consistency conditions. You say, my memory is not going to be sequentially consistent because I can't afford a round-trip thing. I'm not going to do two-phase commit on my distributed database because I can't afford this sort of thing. But once you get into that area, that's a very kind of dangerous area, and you have to know exactly what the application domain demands to know what you can get away with. So it's hard to generalize about that. So Oracle has made tons of money by basically ditching serializability and going with snapshot to consistency. They don't make a big fuss about it, but serializability is something that they view as ivory tower correctness condition. Although you might have to read their brochures carefully and do what you tell that. But same sort of thing is probably going to happen in distributed and parallel computing in some form.
So I'm wondering whether one part of the answer could be, beyond what you already said, that solving computational problems that just require a lot more computation that can be easily parallelized is part of the answer, right, to what will we be doing with the better washing machine. So one particular instantiation of this argument would say, NP-hard problem solving is something that people used to think doesn't really matter very much other than for theoreticians because we can't do it anyway. A bunch of crazy practitioners have gone and done it. Now it's starting to have a major impact in practice. There's a major need for it in practice. More and more people do it. And lo and behold, that's exactly the kind of thing for which Amdahl's law doesn't give you bad news. So I'm kind of wondering, what's the story there? Do you think that, first of all, do you think that this is part of the hope? Secondly, to the extent that this might be part of the hope, to which extent does transactional memory, locks, and so on really get us further ahead there, as opposed to the simple style of run the thing multiple times in parallel with some randomization or whatever variations, right, and in the heuristics, and you will get nice speedups without any shared memory transactions, without anything, just the plain old way.
Oh, certainly if you can get away with that, then by all means you should do that. But what might happen is you might say, well, I want to run these parts in parallel and then put a barrier here and start doing more sophisticated things, and then you're back in the danger zone where you have the feeling that some amount of synchronization and coordination will pay off, possibly in terms of not duplicating work, using those resources for other things. But this will only pay off if you can figure out how to do that well. And so transactional memory and locking and all of these things, we're really talking about engine room level mechanisms. Yes. That it's not going to tell you what you want to do. It's going to say, once you know what you want to do, this may be a better way of doing it than the way we do things now. But I still maintain that you're probably going to need some kind of synchronization no matter what you're doing. And getting that right, whether it's by this or some other mechanism we haven't even thought of, is still going to be one of the central bottlenecks. We're still talking speed of light issues here.
Yeah, I guess, I'd buy transactional memory. The only thing I'd worry about is, again, it's a model that doesn't account for any cost to communication. And how, it just seems to me that's the real question here, right? I mean, you have to be able to you have to be able to organize your computation in such a way that you're not doing too much communication. And I don't see that in transactional memory. So somebody's either is going to be done automatically for you, which would be fantastic, or there's some model.
I think the kinds of mechanisms that you want to keep communication under control. And again, this is really, when we talk about NUMA, what we're really talking about are communication and costs. I think in this case, the best thing you can hope for is that transactional memory won't get in your way when you organize your computation to you say I'm going to co-locate this thread and this data so that I don't create cache traffic. Then you want to make sure that any synchronization you have to do works well. But you don't want the synchronization mechanism to force you to place data in certain places and do all of these difficult things that modern architectures are forcing you to do. So in some sense, it's a little bit of a feature that transactional memory doesn't address this, because it means you can go ahead and address it any way you want. And the synchronization mechanism, at least in principle, aspires not to get in the way.
But doesn't parallel computing almost mean that you will have to address communication at some point as things scale up?
So in the kind of multicores that we work on now, that's just over the horizon. So in clusters and so on, of course, that's a big deal. But if you're looking at a Niagara or one of these new Intel machines, it's still the case that cache coherence traffic is a big issue, but the memory isn't quite NUMA yet. And so the next generation, this will hit big time, and then we'll have to go back and redo things. But right now, we're not borrowing trouble by addressing that. But that would be great. That's what the next generation of grad students should be looking at.
But isn't that model, in some sense, part of the problem? That is, in some ways, I think we got into this parallel processing problem where we are now because the computer architects did such a great job of making every computer in the past 40 years look like an IBM 360. So we wrote all of our data structure and algorithm books for an IBM 360, and everybody in this room knows how to program an IBM 360, and nothing else. And then what happened is that all the fictions of the IBM 360 broke down. Memory is not as fast as the processor. Wires are expensive, and we care about the power bill. So all the abstractions of the 360 broke down, and now we're having to cope with it. And now the architects now try to provide for the programmer a model that says that all communication links are the same, which is a complete denial of the fact that we live in 3-space. So now, is it that we're going to build a computing model that says that all communication links are the same because that was an easy abstraction, and then 5 or 10 years later come back and tell the programmers, oops, we discovered we lived in 3-space. That's not true after all.
The first thing I tell my students in my multicore class is that all the abstractions are broken. That you can't, you have this shared memory abstraction, which is beautiful in principle, but if you believe it, then your program is going to have terrible performance. And you have to outwit, in some cases, the underlying cache coherence algorithm. But the reason the abstractions are broken is we haven't figured out how to do the right ones yet. And so eventually, some kind of consensus may emerge, but I'd be extremely reluctant to say, well, let's discard this particular model and jump to something that's radically different. Because every time we've done that in the past, it hasn't worked out all that well for us. So I think the critique is perfectly on the money. It's just I don't know of any alternative. So we're kind of muddling forward with the architectures and abstractions that we have today.
So you made the analogy between transactional memory and automatic garbage collection. So garbage collection solves a lot of problems for you, but it also introduces other issues. So it makes it harder to reason about your code, so you can introduce bugs through having cycles in your memory graph. So are there things that transactional memory would also introduce in a similar way? Like, does it make it harder to reason about synchronization, for example?
So there are issues with, for example, how does transactional code interact with non-transactional code? So if you're running a software transactional memory in a managed language like Java or C#, that's not much of a problem because you can mediate everything. If you're writing it in C++, where where you can take a pointer, hash it, add 17 to it, and then store into that address, it's very hard to give a meaning to that kind of program. On the other hand, you can't have halt and catch fire semantics because an Intel won't. We'll call the security guards when you come and visit. So there's all kinds of problems of that nature. I have a PhD student who did a thesis on debugging software transactional memory, and that's actually easier because unlike p-threads and locks, the runtime system has its finger in all the synchronization and recovery areas. So you can instrument anything you want, and you can catch things like silent writes. If I write 1 to a variable that's already 1, then I've created a write conflict that doesn't need to be there. And so transactions make it much easier to debug things, but it's true that they will introduce new kinds of problems, particularly performance problems, which aren't terribly well understood. But again, for grad students, this should be good news because this is stuff that you should run out and get to work on tomorrow morning. Bill.
Of course, I was wondering what research has happened, sort of from a software engineering perspective, sort of support for programmers who want to write in a transactional memory style. So, for example, it'd be easy to do some really stupid things, like say atomic to a third of my program and just kind of break it up into thirds.
Atomic void main is a really bad idea.
Yeah, exactly. Or like a third of it and do that 3 times. So that's obviously stupid. So the point is that to get whatever parallelism, to get as much synchronization as you can, you have to put the atomic brackets in reasonable places. And it would seem like what reasonable means is really about performance. So you need some kind of software engineering feedback loop. And it would be great, for example, to have some kind of part of your IDE which said, here's some data structures which are causing you some problems. You might need some atomic operations around X, Y, and Z. So, for example, something that would point out those lame counters. Right?
What you need is a profiler, basically. And so the same student who did the PhD on debugging, we wrote a paper on profiling software transactional memory. And there, again, for the same reason that software transactional memory basically mediates all of the synchronization issues, you can put a kind of a sensor anywhere you want, which is something that's very hard to do if you're using kind of off-the-shelf synchronization. Beyond that, there's some patterns like if your transaction is aborting, it's because there's a hotspot. So you can look at the hotspot and say, well, is this a real hotspot or is this a false conflict? And these are all things that are not very well developed. I mean, I think everyone acknowledges the need for these sorts of things. For hardware transactional memory, debugging hardware transactions is hard because the idea is that if you want to really do this transparently, then you abort the transaction and start over again. But then by definition, you couldn't see what happened. It went into a black hole. That's not what you want for debugging or for profiling. And in fact, one of the flaws of Sun's rocket processor was it was annoyingly vague when it aborted the transaction why it did that. And particularly it was hard to tell, was this a synchronization conflict that means I should retry it again, or is this a no way we'll ever commit a transaction that used too many resources? And in fact, that's one of the subjects in the paper that I mentioned that the Sun people wrote about their experiences. So I think this is all something where the need for that kind of work is clear, but it's only just started in some sense.
So I think let's take one more question and then...
How will heterogeneity in cores change parallelization and distributed computing?
So I think it'll make things harder. I think for something like synchronization is kind of agnostic about what kind of core you have. So the heterogeneous core basically means, well, there's some kind of work that should happen over here and some kind of work that should happen over here, which implies that the data should be moved around in certain places. But that isn't really a synchronization problem. That's really more of a kind of overall engineering problem. And here, too, I think the best you can hope for is that whatever synchronization mechanism you use doesn't get in your way. And, I think you would like to have a synchronization model that is oblivious to the heterogeneous aspects so that you can do other things with your heterogeneous processors. But synchronization, one would hope, would not be one of the things that this would have.
But would parallelization become a lot easier?
I think it would be harder because you need to make sure that your graphics processor is doing stuff that graphics processors should be doing, and your floating point processor should be doing floating point stuff.
So you can split your workload into as a cross-grain level itself.
Yeah.
And so that would make parallel programming easier.
It would make parallel programs more efficient. The task of using it is, I think, is still harder. It would make synchronization probably just as hard on a heterogeneous machine as any other.
All right, well, let's synchronize on giving Maurice some